Electric motors make the world go round, or at least part of it. You've already learned about the motor effect and the left-hand rule, so let's put that to some good use. Here's a motor frozen in time. Let's talk through its main components and what is happening before we set it back in motion. I always like to start at the battery, which is down here with the positive terminal here on the right. Electricity will flow along the cable up here to this brush, onto the commutator. We'll come back to that later, and along the coil, round and back again, through the commutator, onto the brush and back to the battery. One complete circuit. Right then, that's the electricity. The magnet is just going to sit there, so we have a field going from left to right as shown by the light blue arrows. And that leads us to the motor effect. Let's look at the left hand side as it's easier on your hand. First finger field, second finger current gives us thrust upwards. Let's walk through the animation. So when the coil turns, the commutator slides across the brush, like so, until it stops touching the brush and the current is cut. But it keeps turning due to Newton's laws, until the commutator touches the other brush and completes the circuit again. It has now turned 180 degrees. If you follow the current again, you'll see it is taking the same path around the right to the left and back. Let's complete the full turn. And done. Back to where we started. Now then, if the coil was to rotate like shown, and everything was connected like a normal circuit, the wires would get tangled up very quickly. And that's where the commutator and brushes come in. So let's take a closer look at those. At the moment, there is no electricity flowing. The positive terminal of the cell is connected to this brush over here, and the south terminal is connected to this brush, but the brushes are not touching anything, so the circuit is broken. To get a motor like this started, you need to give it a push sometimes. That's better. Electricity flows out of the positive terminal and onto the brush. The brushes brush against the purple commutator, allowing the electricity to pass across, but they are not physically attached. It's like how your toothbrush touches your teeth, but it can slide around easily, but with electricity. We've now got a complete circuit, so the electricity flows in the magnetic field now, and that gives us that thrust. So when the coil turns, the brushes still contact the commutator and the coil continues to spin around its axis. But eventually the brushes stop contacting the commutator, and now the circuit has been broken, so the current stops. If there's no current, our second finger has nowhere to point, so the motor effect stops. Newton told us that objects with mass will keep moving though, so the coil will keep spinning for a while. So the inertia or momentum keeps it turning until we get contact again. So whichever way round the coil is, we still get the forces acting in the same direction. So, as long as we keep supplying current, the motor will spin forever thanks to the split ring commutator. It's called a split ring commutator because it allows electricity to flow, like commuting I suppose, and it is not a complete circle. It is a split ring. Let's see it in motion again. There it goes. This time I've added some arrows to show the direction of the force. You can see how the force always acts upwards on the left and downwards on the right. And you can see how the motor can just spin and spin and spin. If we want to make it faster, we just need to make the magnet stronger, or add more turns to the coil, or increase the current. And that is the DC motor.